Yeah, good evening, everyone. Sushant Camp. So let's start off. So last thing we were doing reflection. Yeah, camps on everyone. So the second part is refraction. So like we discussed in the beginning, the reflection and the refraction are the two phenomena. In reflection, we have done plane mirrors, spherical mirrors, the graphs, and all that stuff. So the second part is the refraction. Let's see. First, let's define refraction. So what is refraction? The bending of light rays at the interface of two mediums. Right? This phenomena is called refraction. So we define something called a mu, which is refractive index. This is nothing but the ratio of speed of light by speed in vacuum by speed of light in medium. And we know the light travels fastest in vacuum. So we will simply call it C vacuum by C medium. So the refractive index mu is always greater than equal to 1, and mu is equal to 1 for vacuum. So we can also write like this thing: the speed of the light in a medium actually decreases, becomes C vacuum by mu. So this is one. Few things here. Whenever the light travels from one medium to another medium, the frequency remains same. Frequency does not change when light goes from one medium to another. Meaning, think about it. Let's say if there's a red color bulb and you're seeing it red, and if you go into the swimming pools, it still looks red, right? Color doesn't change suddenly. So color is a property of frequency. So frequency does not change when light travels between different mediums. So speed will change, frequency won't change, but it becomes like this. So lambda will change, wavelength, lambda medium becomes lambda vacuum by mu. Lambda is wavelength. So whenever light travels from one medium to another, wavelength and speed will change, whereas the frequency remains constant. Have a look at this.
So the wavelength can't change so much that the color of the light becomes different, right?
Color depends on the frequency, not on the wavelength.
Achha.
Color is a property which depends on the frequency. It's not a property of wavelength. Since the frequency doesn't change, the red color will remain same, or the blue light, whatever you're sending, the color will remain same. So you can add that point also. Color depends on frequency. Mostly a CET level question. Who is absent? Ali is there. Someone else is missing. Clear, everyone? That's a basic idea there. So the speed of light actually changes when you go from one medium to another. So using this property, let's see how it works. So let me ask you a question. How does an aeroplane take a turn? This is something which we discussed in foundation. Anyone remembers? How does an aeroplane take a turn? Meaning, what is the mechanism? You do something, when you rotate the rudder or something, something happens and the plane rotates. So what happens exactly? Anyone? Same thing,
One side
even
is kind of slowed down and the other goes with this with
how will you
some.
do that? How will you speed up one side and slow down the other side?
So the direction of airflow is changed.
Here, you will change the airflow in the atmosphere.
No, no,
Sorry,
no, sir, no, sir. It's like there is an airflow on the aileron, so that's why when you
You
change the
fly at an
direction,
angle, right? Like wings go up slightly on one side.
nee, that you're talking about flaps actually. That doesn't, it does affect, but not that much. You can't make, very large turns. Like what Yasha was saying, right? Make one side go faster, one side slower. You can do that by a flight simulator, it seems. So I'm talking about a real plane train, not a simulator. So what we do that, right? We have in a plane, if you see the engines, right? We increase the thrust on one side, we decrease the thrust on one side. You create a differential. So if there are two engines here, if you increase the force on this engine, what happens? So this side of the force is more, this side of the force is less. So this side will travel more, this side will travel less. So the plane becomes like this, isn't it? This is the same concept that happens in your vehicles also. Whenever you're going on your car and you're taking a right turn, what are you doing exactly? When your car is going on a right turn, you know what you're doing? The wheels on the left hand side are rotating more compared to the wheel on the right side. So this will travel more distance, this will travel less distance. Once you got the required angle rotation, make them equal again, then the car will go in a straight line. So normally we think like this, right? The front wheels are not connected, okay? The front wheels are connected something like this. They're not like this. Both the wheels can rotate independent of another. It's a differential gear, we call it. So basically, the main idea is that why all that? Just observe yourself when you're walking and take a turn towards left or right. How do you take a turn? When you're walking, and if you want to take a right turn, observe what you do. Your right side leg will actually slow down. It almost stops, and your left leg swings around it. Isn't that what you do when you're taking a right turn? You're walking, and suddenly you want to take a right turn. What you do? You put your right leg like a pivot, like a base, and about that point you rotate your left leg. So getting it. So whenever you have to take a turn, in doesn't matter which concept it is, aeroplane, you walking, or I don't know if someone is here in NCC. If you see people in NCC, right? So let's say they're in a file here, and let's say they're marching here. And when they say about right turn, the guy on this corner is simply, at the same place he's doing left, right at the same place. And this guy is walking here. Once he comes parallel to this guy, then the line moves again. They all don't walk the same thing. The guy on the leftmost edge will have to go much faster in order to be again parallel. The next time when you observe an NCC march or something, right? Observe that. Whenever they're taking a turn, there's a difference in speed. The people on the right side or the left side, whichever direction you're turning, they slow down and the other side goes faster. So what does this have to do with the light? Same thing. So if you take a medium here, let's say this is air and this is water. Some medium, okay? I'm just taking something here. So in air, the speed of light is more. I'll just do one thing. Let's say this is mu1 and this is mu2. We'll derive this. Okay. So, and let's say we have a wave traveling like this. So we have a light beam coming like this. So let's call this thing point A, and let's call this thing This is point B. Okay, it's like a light beam. AB is coming this way. So it was supposed to travel in a straight line. Like this. So on this side, the speed is c by mu1. On this side, the speed is c by mu2. So let's assume the mu1 is, greater than mu2, or mu2 is greater than mu1. Now see what happens here. The moment you enter this region here, you actually, let's say mu2 is greater, mu1 is less than mu2. So this light ray which is inside will go faster. So by the time this B travels from B to B dash, the light ray will travel from A to A dash. It will travel much more. And now if you join them, this is what the light beam happens. So the light beam which is supposed to go this way, now it actually starts going like this. So we are assuming mu1 is greater than mu2. Means you're going from denser to rarer. I'm sure you studied this in school. Whenever a light ray goes from denser to rarer, what happens? It goes away from the normal. Did you see how did the light ray bend? So what is happening, when you're entering, some part of the wave is traveling slower and some part of the wave is traveling faster. This makes that entire wave, to take a turn. That is what is this thing, the bending of light ray. This is the reason why the light ray bends. Think of like this. Simple example I'll give you. See, let's say we have a road, and for some reason, right, this entire road is made of mud. And if your car is coming, with full speed and enters the mud, what will happen? Won't the car on this side get dragged? It slows down, isn't it? So what do you think will happen to the car? As it is entering the mud, the right side is traveling faster. The left side will actually start slowing down. Won't the car start becoming like this? And by the time it comes out of the mud, it actually becomes like this. Because the right side got slowed down, left one traveled more, the car would actually drift this way. Is this making sense, everyone? So if you look at the points here, this is your angle of incidence and this is your angle of refraction. That is R. And if you look at this triangle here, triangle A, B, B dash, if that is I, this is 90 minus I, this is I, and this is 90 minus R. Sin I is BB dash by AB dash. And we know BB dash will be the speed of light c by mu1 into time. Similarly, in the triangle A dash, B dash, cos 90 minus R will be adjacent side. That is A dash by AB dash. Again, A dash is the speed of light c by mu2 into time. And if I divide these two, we end up with sin I by sin R, which is BB dash by AA dash. This is c by mu1 time by c by mu2 time. This thing is mu2 by mu1. Cross multiply. Mu1 sin I is equal to mu2 sin R. This is your Snell's law. Of refraction. I'm sure you studied this in school. Mu1 sin A is equal to mu2 sin R. This is how it is derived. Have a look at this. I could have taken the other case also. It is slowing down. In that case, you know how it would look? This guy is traveling like this. So by the time this thing travels from here to here, it was going in a denser medium, it will travel less. So this is how it looks. It would have been this way. In this case, it would have been towards the normal. Either way, I could have proved it. It's the same thing. Have a look at the proof. It's a good one. Udian, Mehan, keep your cams on. Again, we just use simple logic here, and there's nothing there. By the time the light travels from A to A dash, the light also travels from B to B dash. For A dash and B dash is equal. Because it's the same light ray. Please check it out. Clear with the proof, everyone? So this Snell's law mu1 sine and mu2 sine are right. We just didn't dream about it. We have actually proved it. What you're talking, right? Bank left, bank right is what? What is that? Clear? Next page. Now from here, so let's say this is mu1, this is mu2, and let's say mu1 is greater than mu2. Means you're going from denser to rarer. So, and if you send a light ray, the light ray will go away from the normal. Vice versa. If mu1 is less than mu2, you're going from rarer to denser. And if you send a light ray, this actually gets closer to the normal. I is greater than R, here I is less than R. Now, in this scenario, if you just keep on extending the, this angle, if I kept on increasing, at a critical angle, call it theta C. Again, we are talking about this case, mu1 greater than mu2. This light ray will hit this and become parallel. This angle is called theta critical. And if I becomes greater than theta critical, then basically the light ray simply bounces off. Like a mirror. So the interface behaves like a mirror. This phenomena is called total internal reflection. Again, remember this happens only when you go from denser to rarer. Or you simply call this as TIR. Check this out.
So,
We know.
is there any particular reason why it happens when you go from only density to error?
Think, na?
Okay, so when you go from dense it bends toward.
Then towards the normal. So reflect कैसा होगा ना? This thing is like going away. At one point it bounces off.
Oh,
It has to go from denser to error because the other case you will go towards the normal. Check this out. I'm sure you have done all this stuff in school.
Yes, sir.
Rarer to denser, denser to rarer, and all this stuff. So here, if you apply this Snell's law here, so this angle is 90. So mu1 sine theta critical is mu2 sine 90. So we get sine theta critical is mu2 by mu1. Check it out. Okay, from normal towards normal.
Sir,
Right.
sir, in the second case at the critical angle, the refracted ray would be perpendicular.
It'll be parallel to the interface and perpendicular to the normal. You're taking
So-
angles with respect to normal, right? This is the normal.
Yeah, in both the cases it will be parallel,
What is the second case?
like from rarer to denser.
Rarer to denser. That would be reverse, na? If you're sending a light ray parallel, then it will come out like this.
Okay,
In that case, the incident angle will be 90, not refracted angle.
okay.
Is that what you're asking?
Yeah.
That's a different thing, Aryan. Search online. Mil jayega. That has nothing to do with light. So that's not it's based on differential. Clear, everyone? But there is one thing important here. What do you mean by denser and rarer? We are saying mu1 is greater than denser, mu2 is this thing, the rarer, all great. This, you can see it in waves also, but try to understand here. A medium is said to be optically denser. Now, this has nothing to do with regular density. This is called optical density, basically. Optically denser. If the speed of the wave is more. Similarly, a medium is said to be optically rarer. The speed of the wave is less. Let me give an example that will make it better. Example. Let's say you're going from air to water. And if you send a light beam, so which one is light goes faster where? Air, right? So if you send a light beam, for light beam, air is rarer and the water is denser. And when you go from rarer to denser, the light ray will bend towards the normal. The same thing you do with sound. Sound travels faster where?
And water.
Water. So if you use a sound thing, even sound is a wave. Even sound obeys, all law of reflection and law of refraction. Sound travels faster in water, so this is rarer. This is denser. So if you send a sound wave, it goes away from the normal. Clear with this? Yeah, so sound travels slower in air. Sound travels faster in liquids. Sound travels even faster in solids, right, Anika? So for sound, so this is the question then. So is air denser or rarer? It depends on the whether it is light or sound. So be careful with that. So don't blindly mug up like, air is always rarer. It depends on the what kind of wave are you using. Are you using a light wave or a sound wave? So even sound obeys law of refraction, but the only difference is rarer and denser ka whole concept will get reversed. So be careful with this. Clear, na, Anika? Got this?
Sir, the optically denser you have written the speed of wave is more.
I wrote reverse. My mistake. Speed of the wave is okay. That's what you're saying. I got your point, Anika. I wrote it wrong. My mistake. If the optically denser meaning speed of the wave is less, optically rarer means speed of the wave is more. Please check. So this is one thing. Keep in mind. They can ask you the sound also, and things will be different.
Then sound obeys that Snell's law.
It obeys Snell's law. You can apply Snell's law for sound also. There, we are using a light beam here, and that's like a protractor. So if you see the light rays entering straight, so here where is refraction happening? We are interested in the refraction on the flat line, okay, the horizontal surface. So initially I is 0, R is also 0, light ray is going along the normal straight. Now if you start bending it, you can clearly see here, angle is almost, I is how much, 25, R is how much, 40. The light ray is going from glass to air. It is going from denser to rarer. So light ray will go to away from the normal, isn't it? You're getting it? So light ray is going away. That is interface which is there. That's your normal there. And now the angle is 30 degrees. Angle is 30. R is almost around 46, 47 के आसपास था वो. You can actually see there's a reflected ray also. Because it's not exactly an ideal case. Some of the lights already started having TIR. The light ray is becoming flat. This is the critical angle gone. Meaning at somewhere at 40 getting critical angle. You can see there is no light ray on the other side. This is the total internal reflection. That slab is behaving like a mirror on that edge there. I think around 41, 42 degrees is this. If you continue to increase the angle, it will just be like a mirror. And the best part is that refracted, there's not a single ray on the other side. It's completely dark. I know there is some dispersion light is going on, but
Our school teacher showed us the exact same video.
Clear with this, everyone? There. So you can just add up here. Theta critical is sine inverse mu2 by mu1. Great. Let's see a question. We have a normal here. Mu1 is greater than mu2. This is mu1. This is mu2. We are sending a light ray at an angle I. So there'll be refraction and everything. Plot delta versus incident angle. Delta is the angle of deviation between incident and the refracted ray. Now, what do you mean by that? After hitting this, so let's say example, mu1 is greater than mu2, no? So it's going from denser to, it will become like this. So this is our, so the light ray would have gone straight like this. So this is the deviation we are talking about. The angle, it should have supposed to go in a straight line, but because of this refraction, it got bent toward away from the normal. This is the deviation. So approximately plot the deviation versus angle of incidence ka graph. Exponential ka na. Think it's a good one. Parabolic. Can't say that, but let's see. Try. 1 more minute, then I'll show you. There are two parts in the graph. If you figure that thing, then you got it. Let's see. There are two parts in the problem. The first part, This is I. This is R. The slight ray should have gone like this, and this is the deviation. So delta would be R minus I. And we know from Snell's law, mu1 sin I is mu2 sin R. So R would be sine inverse mu1 by mu2 sin R minus I. This is one part, okay? The second part of the graph, let's say if the angle becomes greater than theta critical. So this light ray will simply bounce off like this. This is I. This is also I. The light ray would have supposed to go like this. This would be the deviation delta. In this case, delta will be 180 minus 2I. So there are two parts in the graph. So when you plot this, delta versus I, one thing is sure, right? When I is 0, deviation is 0. The graph starts from here and it definitely increases till theta critical. That after theta critical, it should be discontinuity. It's a sine inverse function. It's an increasing function here. And then at this point, now see what happens. Just try to understand from the diagram perspective. Exactly at theta critical, you're like this, isn't it? So this was the deviation. Even if you increase by 0.1 degree, suddenly doesn't the beam become like this? Means the deviation suddenly bumped up to this level, right? So there's a discontinuity. So the graph will start at a higher level and then it's a straight line. So at theta critical, the graph will have a break. It's a discontinuous graph. Look at this thing. This is a line equation. This looks like y is equal to mx. Delta is equal to minus 2I plus 180. Y is equal to mx plus c. This is a straight line. This is a sine inverse graph. This is messed up. Check this out. So it's actually an increasing function, and then there's a discontinuity, and then it decreases at a linear rate. It's not a parabola, but yeah, it looks like one. Hope everyone's clear with the graph. Standard question. Check it out. Clear, everyone? Any doubts on this? Vartika, Ali, got this? Neil, clear? Arjun, Aryan,
Yes, sir.
Swastika, clear with this? Mayresh, clear? Rehan, Anika, all clear with this? Next one. Let's say we have a glass sphere. Mu is equal to √3. This is the center. And you send a light ray like this at an angle 30 degrees. Find the angle of deviation. Outside is 1. Meaning the light ray will go like this. You're getting it? It'll bend, it'll hit, it'll go off like this. So I want the angle of deviation between this light ray and this light ray. So this will be the deviation ESA. Whenever this angle of deviation is between the initial ray and the final ray. Let's get this. Any answers? 30 degrees. Yeah, one answer. Others, what a minute more. Get it, it's pure geometry. See. So once this thing enters inside here, what is this angle? Snell's law, mu1 sin I is equal to mu2 sin R. So this is 1 sin 30 root 3 sin R. I think I goofed up the numbers. I got your point. Wait. Let me change something. Make this 60. That's what you guys are not getting. Numbers are bad. Change the number, make it 60. Now you'll get. Try. I'll give you a minute now. You can get it, but okay. Point is not that. Make it 60. 60, I think will, yeah, 60 will give you a decent number. Otherwise, you need to keep your cams on. Udayan, Alaksh, keep your cams on. $60, okay. 60, we have multiple 60s, let's see. So this is 1 sin 60. This is root 3 sin R. So we get sin R is equal to so R is equal to 30 degrees. Now understand, R is 30 degrees is this angle. So from here, this will go and again hit the something here. This is the normal. Since this is an isosceles triangle, if this is 30, this is also 30. Again, from Snell's law, this will be 60. You're getting that? So this is 30, so this is 120, so this is 60. That means this light ray is coming out parallel actually. Isn't it? This light ray is coming parallel to the diameter. So now extend the light rays here, you'll observe. So the initial, so this was the diameter. This was the incident ray, which was making an angle of 60 degree. This is the final ray, which became horizontal. So this is delta. 60 degrees is the angle of deviation. Check. Clear everyone how to see? So just, there are two vectors, just extend them and make them meet. And find the angle between them. Clear everyone? Next one, turning the page. Next one is a good one, let's see. So we got a swimming pool or a lake. Depth is d, refractive index is mu, outside is 1. At the bottom of the lake, you kept a bulb. The bulb will give light in all directions. The power of the bulb is P. So something happens here. We have an observer on the outside surface here. So generally what we expect is the entire lake, the swimming pool should be illuminated with light, but we don't see that. An observer on the surface sees a patch of light. Patch of light on the surface. Now you need to think why you're seeing a patch of light. That's the first thing. So find the area of that light patch. And how much power escapes the water surface. If the total power of the bulb is P, how much power escapes the water surface? Let's get this. So the entire bulb ka power is P, how much power is coming out of the water? Something is happening there. Some power is not coming out. I hope the question is clear. So first thing you need to understand why this guy is seeing a light patch. Why doesn't he see the entire surface is illuminated with light? Once you figure out why he's seeing a light patch, you need to find that area. And you need to tell me how much power is actually going out of the water surface or liquid surface. Think, take a minute, and then I'll explain the first part. राइट अद्रित, लॉजिक तो वही है, अभी कैलकुलेट कर रहा हूँ. एरिया इज पाई, ना एरिया इज नॉट पाई रे. How did you get answered pi without r and all? First thing, let's see what is happening. Why are you seeing a light patch? So this light ray, which is straight, this will just come out straight. There's no problem. This light ray will hit, and there'll be a little refraction. This will become almost flat. After this point, any light ray which hits the water will simply bounce off. That means the last light ray which leaves the water will make a critical angle, theta critical. Isn't it? This is the reason. So this will same thing will happen in all the directions. So you will see only light coming from this region, which is a circular patch. Is that making sense? So the last light ray which hits at a critical angle, that will become parallel, and after that done, no light rays will come after that. So once the light rays hit the interface at a critical angle, the light rays incident at an angle greater than theta critical do not come out. So this is what happened. So this is theta critical. This is radius. This is depth. So tan theta critical is r by d. And we know sine theta critical, in this case, it is mu. Sine theta critical outside is 1 and angle is sine 90. So sine theta critical is 1 by mu. Opposite side is 1. Hypotenuse is mu. This is root over mu square minus 1. So tan theta will be 1 by root over mu square minus 1 is equal to r by d. So from here we got the radius of the circular patch. And the area will be pi r square. Check. This is the area of the light patch that you see from the surface. So what you see is a cylindrical thing there. Is this making sense, everyone? Please check. It's a cone of light, yeah, but it becomes. That means if you have a fish living in the water, how does the world look for the fish? See, if there is a fish here, when the sun is rising, the light rays will come this way. So this is the first light ray that it will see. That means it will think sun is rising from here. When the sun is setting, again the light rays will come like this. So the fish will think sun is setting here. So in the fish ka world, the sun starts from here and goes till here. So a fish ka world, right, will look like as if the edges are compressed. Ever heard about a fish lens in cameras? That's what happens. If you take a photograph with a fish lens, the edges will get compressed. If you see in lenses also, right, you have an ultra wide lens and a fish lens. Ultra wide lens will, even the edges will come fine, but if you take a fish lens, the edges will get compressed actually. So this is how the world will look like for a fish. For a fish, the entire world will look like a cone. Getting this thing? So yeah. So for anything living on the water, the world has a different perspective. Abhi the question hua nahi, how much power is escaping? That means if some of the light rays bouncing back inside, means some of them is coming out. So total power is not going out of the liquid. Nah, it's not 50%. You really think with this kind of values, R, D, mu and all, you still get such a good number? Think. We'll give you a minute. I told you this will come again. How much power escapes out of the liquid? Anusha, you got that right. Abhinav, you're right. Others, do check it out. Hmm. Any doubts? Anyone not clear with this concept? Please ask me here. Anyone not confused with what is happening here? Malika, clear with this? Venkatesh, got this? Yasha, Udayan, clear? Great. Three p by two. अरे think about it logically. आपके पास total power कितना था p? How can more than power p go out of the liquid? When you're saying an answer, think na, is it making sense? Do you remember this thing? The area of a surface area of a sphere, surface area of a part of a sphere. Now see what is happening here. I'll tell you. When you take this bulb here, which is power p, this is traveling in all directions, isn't it? I know, niche there is a ground, but technically speaking, if you see this, so the power is being transmitted in all directions. Power spreads out spherically in all directions. Niche there's a ground, so that will get absorbed. So that is wasted actually. So can I simply say like this? So for an area of 4 pi r square, we have a power p, right? Now, in this case, when you took the bulb here, and you're only interested in this much of the angle, meaning you're talking about out of all this sphere that you have, we are interested only any light ray that comes from here. So it's like gone. It's like gone. It's like gone, gone, and gone. So we are interested only in this part of the sphere. Is that making sense? The light rays were equally distributed in all the directions. But when you take this cone here, the light rays which are escaping out is nothing but the light rays which are traveling through this part of the sphere. And this angle is theta. Remember what is the area for this? Told you this will come. We did this in friction, remember?
Pi r to 1 minus
2
cos
pi
theta.
r square, 1 minus cos theta.
Yeah.
This was the question. A part of the, dust is sprinkled, a part of the sphere is covered in dust, find the area. This is the formula, 2 pi r square 1 minus cos theta. Calculus page 115. Told you this will come again. So that area will be 2 pi r square 1 minus cos theta. Where r is this radius we're talking about. Or I can just take it as some. Two pi a square. So then unitary method, think about it. So for 4 pi a square, if you have a power p, for 2 pi a square 1 minus cos theta, how much power you have? So this is the power escaping. So the power escaping will be p by 2 into 1 minus cos theta. This theta is theta critical. Clear, everyone? And what is theta critical? Here, from here we can get cos theta critical. Cos theta critical is root over mu square minus 1 by mu. So that we need to substitute here. This much power is escaping the liquid. Is this logic making sense, everyone? Because when the light rays are going in a sphere, all the light rays which are escaping through this cone will pass through this part of the sphere. Basically, these light rays are escaping out. Every other light ray is bound inside. So for the full sphere, 4 pi a square, if the power is p, then for an area of 2 pi a square 1 minus cos theta, what is the power? So you have to basically use area C, this thing, what you call the area. Again, you forgot this thing. You should definitely go back to calculus and check this out. Remember this thing. This will again come in electrostatics. We will use this at least another 3 times. If you know the result, it looks easy. If you don't know the result, it's actually complex. Any doubts on this? And you want that result, I can just show you in case there. This is how we do, remember? At an angle alpha, take a thin strip. So that strip ka radius will be r sine alpha, thickness will be r d alpha. If you cut it, you get a rectangle whose length is 2 pi r sine alpha and the width will be r sine alpha. So this is the area of one strip. And then we integrate all these things from 0 to theta. Then we get the total area, 2 pi r square 1 minus cos theta. Check it out. Main thing is getting the elements. Once you get the element, it is easy to handle from there. Quite a useful result. Clear? Great. Next one.
So can you go back for a minute?
Hmm.
Yes, sir, thank you.
We got a glass slab. Mu. Thickness is d. Outside is 1. And you sent a light ray inside. At an angle I. So then what happens? Something happens. So light ray will go inside, will come out like this. Find the angle of deviation. And the lateral shift. What is the lateral shift? It's the distance between the initial and the final ray. First, find the angle of deviation. Meaning, first draw the path of the light ray. I think if you draw the path of the light ray, that will show you.
But we don't know which one is which medium, right?
Meaning?
Like denser or rarer.
Outside is 1 array, God.
Oh, right. Yeah.
So glass slab has to be greater than 1.
Okay.
Get this. This is an easy one. This is a standard question. The next one is actually based on this. This is like a base. Get this. Just give it a try. I'll just get some water and come. Right. Deviation is 0. The light ray actually becomes parallel.
The lateral shift is matlab how much
I'll show you. Basically, light ray would become parallel, na?
Yeah.
दो parallels का बीच का distance.
अच्छा.
Let me show you how it looks. So once this guy enters, you're going from rarer to denser. So this would be like this, and this would be like this. So if you see, if this is R, this is also R, alternate angles. If that is R, this is equal to Y. So if you actually extend this light ray, na, so here the delta is 0. So I'm asking you distance between these two lines. This is your lateral shift.
Okay.
Got it? So here, if you see the deviation is 0, the light ray comes out parallel. Check it out, everyone. If you enter with I, you will go inside with R, and then that is also R, so you come out with I. So it doesn't matter at what angle you enter inside. How do you find that lateral shift? So the final and the initial will become parallel. What is this?
In this setup, and we have an through a median of
There.
reflection of 50 degrees.
Can you see that thing?
This setup can also show refraction of light as it passes through mediums of different optical density.
So inside, how is that parallel beam there? The
From
beam
air to water,
deviation is 0. It actually bent inside and came out parallel again.
bends towards the normal, and from water to air, it bends away from the normal. And it also shows that the incident ray and the emergent ray, they are parallel.
So there, it does happen. Arjun, what happened? It is the same video again.
This video was shown to us by.
ठीक है ना? I think we all teachers.
Yeah, all
Assessing.
physics teachers show the same.
How to find this? More of a geometry. D into sine 1 minus r cos r. Yeah, something of that sort. Right, rather 30 seconds more. If you see, this was r. This was I minus r. What you want to find is this. I'll just name these points here. Let's call this A, B, C, and D. So in the triangle ABC, sin r ne cos r would be adjacent side AB by AC. So we get AC is equal to D by cos r or D sec r. Then you go to the triangle ACD. Sin I minus r will be CD by hypotenuse is AC. Therefore, CD is equal to D sec r sin I minus r. That's your lateral shift. Check it out. More of a geometry. Clear, everyone? Easy? Can I go ahead? No, based on this, that means if you have multiple slabs, you'll notice something. If you have a single slab, there's no deviation there. Let's say this is mu1, mu2, so on till mu(n). And let's say outside is mu and outside is mu. If you send a light ray at an angle theta, now see what happens. This would go like this. So this angle will be R1. This angle is also R1. So if that is R1 again, so this will be R2. This will be R2. So basically the refracted angle and the incident angle will keep becoming equal. Eventually when the light ray comes out, again you come out with theta. So what you observe here is the incident mu sine theta Snell's law will be mu1 sine R1 for the first refraction. Mu1 sine R1 will be mu2 sine R2 for the second refraction, and so on. Quite a useful result. Suppose if they say there are 100 slabs and they want the deviation on the 50th slab, there's no need to calculate from 1 to 50. You can directly take mu sine theta is equal to mu 50 sine 50 there. So from here we can write a result mu sine I is equal to constant. Remember, this is valid for parallel sheets. That is, refractive index should change, in a linear fashion. Mu changes, how do we say this word? Mu changes along the normal. Now you got the point. Let's not write that word. It's only valid for parallel sheets. So one important thing here, when you have a slab, how do you know which one is the normal? For example, let's say we have a slab like this. And let's say refractive index mu is 1 plus x square, meaning mu is changing with x coordinate. How is the normal? How are the slabs? As x is increasing, you're getting different slabs, isn't it? So this is how the slabs, for a given x, you have the same refractive index. So in this scenario, this would be the normal. Suppose if refractive index changes with y, that means for a given y coordinate, you have a same refractive index. Means you're keeping slabs like this. In this case, this is the normal. Did you see? Even though it's like a slab only, it depends on how the mu is changing. So the normal is in the direction in which the mu changes. Clear? Others comes on. Clear. Let's see a question. Can I turn the page?
Yes.
Now using this concept, this is the actual question. So we have a region where refractive index mu is given by 1 by 4 plus 1 by y square to the power of half. This is not a good function actually, right? Such kind of, there is a problem with this function, but mathematically it looks fine. Because mu have to be always greater than 1, this thing can create some problems. But ठीक है. So the medium exists only in this region. Only in the first quadrant. So the first quadrant is filled with a medium whose mu changes like this. First quadrant is filled with mu. This is 1, this is also 1, and this is also 1. So everywhere it is 1. So this is the origin there. You sent a light ray like this at an angle of 30 degrees. So once it enters, now what will happen? Do you remember the first statement we wrote there? Light travels in a straight line in homogeneous medium. That means if the mu is constant, light goes in a straight line. Here mu is not constant. So this guy will actually start bending. Find the equation of the light ray. Let's get this. So if you send a light ray through a non-uniform medium where mu is not constant, it won't go in a line. At every point, it is bending non-stop. So it actually starts going in a curve. Find the equation of this light ray. And in circular motion, I taught you something. Whenever someone asks you to find equation in physics, there's only one way you can do that. In calculus, we know slope is dy by dx, which is tan theta. So somehow you have to get the tan theta using physics. And then put equal to dy by dx and then integrate. That is the only way we can do. Try. You got 3 minutes for this. I hope the question is clear. The light ray enters at the origin at an angle of 30 degrees. Mu is 1 by 4 plus 1 by y square ka root. Maybe I can just put a root here. So find the equation of this light ray. I have uploaded 2 practice papers, units and dimensions, kinematics, vectors, laws of motion, friction, circular, work punch, everything, your major test ka portion actually. There are 2 advanced papers in the group. The test will be online till 20. They'll not be graded. It is only for your additional practice. Someone wants to give, you can give. You will start the testing once your break is over again. Friday, is there a festival on Friday? No, right? What is there on Friday?
Nothing.
Nothing, right? Sunday is the festival, no? What are you guys going to do? Find nuclear bombs and blast them? Kuch hai aisa?
Yes.
Nahi.
Oh, so we're
Agreed.
very environmental friendly.
Environmental friendly. So what are you going to do? Burn trains? Nahi.
No.
Or rough trains. हाँ पलक्ष भाई करो. People are violent. How to do this? When is the Tech Fest है बॉम्बे में? Dates आए हैं ना कुछ?
It's in
Yes, sir, they sent on the PACE group
December
also.
mein it is.
When it is? December?
It's in December.
Make sure to go, everyone. इसके पहले पेस का ID card लेना. Whatever your classes का ID card you need. If you have not taken, take it. That is the only time it will be useful. इसका और कुछ use नहीं है. Make sure to go to IIT Bombay that one day, take it as a break or whatever. Go there, roam around, see all the campus, see the classrooms, hostel, jo bhi sab dekh. You need to know what you're studying for. How do we do this? Rehan, come on.
So it's on 27th December.
27 se. Okay. 27, 28, 20 and 30 ke? 31. 5 days.
So 3 days, 27 to 29.
Oh. Interesting. Someone got y is equal to ex square. Nah, listen. How to do this thing? What did I say again? Whenever I ask you equation of a curve, getting it? You need to find tan theta basically somehow. So here, how is the y changing? Y is changing in the vertical direction. So how is the normal? Normal will be in the y direction. So at any instant here, this is your normal. So at this point here, draw a tangent. Let this angle be theta. If that angle is theta, and this is normal. Sorry, why am I drawing normal like this? Normal will be straight. Normal will be like this. So this angle is 90 minus theta. So that means the incident angle is 90 minus theta. Now using the concept mu into sin I is constant. So we have refractive index mu into sin 90 minus theta. What is the initial angle there? Mu is 1. Mu is 1. That will be sin 30 is equal to mu sin 90 minus theta. This is half. This mu is root over 1 by 4 plus 1 by y square, and this is cos theta. So from there we get cos theta. Multiply 2 1 by, just multiply कर लेते हैं ना. This thing is how much? Y square plus 4 by 2y. So we get cos theta is y by root over y square plus 4. So this is theta, this is y, this is y square plus 4, and this will be 2. So we get from there tan theta is equal to 2 by y. And I know tan theta is nothing but dy by dx. So this will be 2 dx is equal to y dy. Integrate on both sides. This will be 2x is equal to y square. Did I goof up something? Y square by 2. Y square is equal to 4x. This is a parabola. Check. This is what I was saying. Somehow draw a normal, get a tangent, make the angle theta. Somehow you need to get this tan theta in terms of mu or the variable, whatever is given, and then put tan theta dy by dx and done. Please check this out. It's a good one. So the lighter will just keep going in a parabolic path. Any doubts on this? Clear? Let's see another type of the same thing, but in a different, it's a little different problem. Let's see. So the previous one is actually a good advanced question, but even advanced, it is like a moderate one. This is more deadly. So here we have a sphere, some opaque object here, and this is your center. And this is radius r. Okay, so this entire region which we have, this is little weird region here. So at a distance of 3r, you're sending a light ray at an angle theta. The refractive index in the region is given by mu of small r is mu naught small r by capital R, where small r lies between infinity and capital R. Meaning here the refractive index changing radially. Equation of the light ray, there's nothing equation of which one you're talking about? This one? This is the equation of the light ray after entering the region. Incident light ray to straight line hoga na? Right? So this is the refracted ray ka light ray. Mu naught is a constant. Small r is the radial distance, mean distance from the center. Look at this thing here. The refractive index is changing radially. Meaning from center, if you draw a circle, this entire circle has same refractive index. If you go out, you have more refractive index. You have more refractive, like onion ka shells. You're getting the difference? Here the refractive index is changing radially. As you go out more and more, you get more and more refractive index. So you notice some constant, r is a distance, capital R is a radius, fair enough. So the question is, so this light ray won't go properly. This light ray will start bending again. So the question is, find the minimum distance between the light beam and the center. I hope the question is clear. So there's a three-dimensional region here. So this blue thing which you have is like some kind of opaque object or something up to r. So this light ray is incident at a distance of 3r at an angle theta to the normal. So this green line here is a normal. Here refractive index is changing radially. So normal will be along the radial direction. So once it hits the region, right, it starts bending inside. Now we don't know the equation. Finding the equation is also difficult because it is 3D. But what I want is the minimum distance. What is the minimum distance between this guy and this guy? Try. Take 3-4 minutes. It's a good one. It's more complex.
So can you explain the question again?
Which part you didn't understand?
So so the part when it hits the normal.
No, you understand. You agree the light ray bends.
Yeah.
So the light ray will go like this. So the distance from here is changing now.
Okay.
So I'm asking what is the minimum distance between them?
So that
Correct.
thing is a circular disc, right?
It doesn't matter actually. That is just there for sake of it. You can say the sphere. We are actually only interested in this R here. It's like some kind of a sphere in the middle. And look at this thing. Refractive index is changing from where? The medium is here, Abhinav. This entire thing is a medium. You're getting it? The sphere is nothing. The sphere is just a spherical object. यहाँ पे देखो, this R starts from R. The medium starts from capital R to infinity. Sure, no?
Yeah.
Still anyone confused? Please ask. Don't hesitate. Get it cleared. But the important thing, we should know where you are confused. I'm sure most of you understood this logic, like light ray will bend. The light ray is coming at theta, normal, itna clear hai. The minimum distance matlab, initially this is the distance, then 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 this is the distance. And then it keeps increasing again. At some point you have a minimum distance. How much is that? I hope the question is clear now at least. Just to give you an information here, mu into sin I is not constant here. This is not parallel slabs. This is valid only for parallel slabs. Mu I is equal to sin I is constant is not valid. So be careful, don't use that formula here. This is applicable for parallel slabs. Think. I have 2-3 minutes. I need to get the relation between mu and r and the theta. Slightly, it's a little difficult, but think. Let me help you with this thing. See, we need to actually go back to the basics again. So for this sphere here, let's say this is R1, this is R2. And let's say this light ray which you sent, right, is something like this. Now understand these are the normals, okay? So this angle of incidence is I, and this angle of incidence is I dash. You're getting? So here the normals are like this, so the angle of incidence is changing. So these green lines are the normals passing from the center. So for this purpose, I gave you that sphere so that you know how to draw normals.
Okay.
The normals come from out of the sphere, na? So सिर्फ उसके लिए use था. Other than that, the sphere doesn't play a big role anywhere. So if this is I, then this is R, and this angle is 180 minus I dash. and that is R1 and that is R2. I'll do one thing. I'll write this as R1 and R2. This is center. Let's call this point A and let's call this point B. So if you take that triangle CAB, I can use sine rule. What is sine rule? The length opposite side by sine R by R2 is sine 180 minus I dash by R1. So from here we get sine R is equal to sine I dash R2 by R1. This is equation 1. Why do we need this now? From Snell's law. So we have two things here basically. So one is geometry and one is this. So I'll tell you what exactly changed, okay? I'll tell you what we did. In this question, this angle was R. And you said because it is alternate angles, this is R, isn't it? Wo to geometry hai na? Because it was a parallel lines, your life was easy. You said this was R, this is R, done. Geometry khatam ho gaya. Then you applied Snell's law. So, but in this case, the geometry is not so straightforward. We had to do something like this. So actually, if you see now, technically we did the same thing, but here the geometry was more complex. So here the Snell's law says mu1 sine I is equal to mu2 sine R. Take the sine R and dump it in this. Mu1 sine I is R2 by R1 sine I dash. But I know already what is this thing. This thing I can shift it here. Mu1 R1 sine I is mu2 R2 sine I dash. Can you see something interesting here? This implies, look at this result. This implies mu R sine I is constant. So for parallel slabs, you've got mu into sine I constant. Na? Yahan pe the refractive index into the distance into the angle of incidence is constant. So we proved this. This is a different result. So the refractive index changes variably with a radial direction. This is the result. So here that formula is not valid. The mu sine I is not constant. That is wrong. That we derived for parallel slabs. Because in parallel slabs, this R1 and R2 both became equal, isn't it? It didn't matter. Here it got goofed up. There, this is the result which we got. Have a look at this.
Sir, do we need to remember this result or this is useful only for this particular question?
This is only applicable for this kind of questions, where the refractive index changes radially. R के साथ change होना चाहिए. Meaning the more away you go from the center, more the mu changes.
If they
So
change
this
it
is
to
not
something
R
like
square हो गया तो गया.
हाँ.
If you change it to R square तो गया. Still you can use this though, but yeah, it depends on this function. But for radial fields, for radial variable thing, you can remember this. It works. Have a look at this, everyone. Once you got this, question is over now. Let me show you. So now getting back to this, I'll turn the page. So initially you're entering from where? 3R. The light ray goes like this and goes off like this. Let this distance be R minimum. Now tell me one thing, at minimum distance, what will be this angle here? 90 degrees, na? The angle of incidence is 90 here. And this will be theta. So now applying the formula, mu1, R1, sin I. Mu2, R2, sin I2. So mu ka formula is mu naught R by R. Mu naught. You can just substitute the formula there. Mu naught R1 by R, R1 sin theta mu naught R2 by R2, this becomes sine 90. Mu naught will cancel. You end up with RR will cancel. R1 square sine theta is equal to R2 square. So R2 will be R1 sine theta ka root. And initially R1 is 3R. And this is your R minimum. This was your R1 and R minimum was your R2. Clear with this? So mu is equal to mu naught small r by capital R. So I just took that mu and substituted here. Check this out. So that's your minimum distance, 3R root sine theta. So theta is that angle given. So the main thing is figuring out this result. No, that's why this is not a standard problem. This is non-standard. The reason why you need to know this is because, blindly don't remember that mu sin is constant everywhere. Just be careful with that part. Don't write mu sin is constant everywhere. It doesn't work. It's only for parallel slabs. You do some other function if you give me, why should the angle be? Anusha, think about it now. If it is not 90 means what? If it is acute means you're still coming towards me. If it is obtuse means you already came towards me and you're going away. Can we use the equation mu and find the equation? This is not a line equation, right, Aryan? This is in three-dimensional curve, isn't it? This is not a line. I hope everyone is getting why the angle will be 90 at minimum. All clear at this page? Can't find the equation of a line. It will be pretty messed up actually. If you want to find the equation of the line, I think this is the line equation actually. R square sine theta, R square sine I is constant. This is the equation of the line in polar coordinates, like equation of that curve in polar coordinates. Check this out. So put it on. So that's the last one for the day. So next class when we meet on Friday, we are going to do apparent depth, right? So we will finish off refraction on plane surfaces this week. And once you come back, then we'll start the refraction on curved surface and lenses. So not much. So we'll wrap up with that on Friday. So Friday, I'll let you know there's going to be a small issue there that they have a passport renewal thing. I should be reaching home by 5 o'clock. If I get late, I'll let you know anyways. Mostly there is no problem. Okay, so with that, we'll wrap up for that day. So make sure to go through these problems again, right? So next week, you're getting a break. So I won't say, study every day, but maybe 2-3 days you can sit and finish off your backlog.